Hello and welcome back, everybody. The section is called Integration by Parts. And the Fourier and Taylor series. So we should start out by noting something very special. That so far, all of the orthonormal bases I've provided for you are finite dimensional. So I've provided cases like 3/5, 4/5, -4/5, 3/5. Or we saw this in the last exercise. We had 1 plus I over 2, 1 minus I over 2, 0, 1 minus I over 2, 1 plus I over 2, 0, and 0, 0, 1. This was, of course, 2 dimensions, 3 dimensions. And even when we were doing some examples of basis decompositions, where I would write some vector decompose, I would say k is in an index set, and then I would say it's the inner product of v against e hat k multiplied by e hat k. Every time we had an example of this, all of our examples were something like a sum k starting at 1 and ending at 3, or something like that. So we weren't doing any infinite dimensional examples here. So today's video is really about the infinite dimensional situations. That's what's going to be this Fourier and Taylor series. Recall the word series refers to an infinite sum. So when we have these summations here that have infinitely many elements in them, that's what the Fourier and Taylor series are going to be. And these aren't the only 2 cases of infinite dimensional vector spaces, but these are definitely the 2 most common. So throughout your entire experience in any sort of higher level math, these are going to be the 2 that get referred to all the time. Unfortunately, to get into them, to describe either in a very well-founded sense, we do have to start with this topic known as integration by parts. And sometimes this is included in a first semester calculus course, and sometimes it's not. It kind of depends on the instructor, what they wanted to include for you. But let's just start with U sub really quick. U sub is really the opposite of the chain rule, in the sense that you'll recall that if we had something like f of g of x, g prime of x dx, you can compute the antiderivative of this just as the antiderivative of f, which I'll call capital F, of g of x. So let's see. This is the antiderivative of lowercase f. So that was U sub, and that is almost always included in a first semester calculus course. Integration by parts is the opposite of the product rule. So when it comes to derivatives, some of everybody's favorite rules of derivatives are the chain rule and product rule. And in fact, the quotient rule is a combination of the 2 of them anyway. So these really are kind of the 2 primary rules of derivatives. And hence these 2 versions of antiderivatives, integration by parts and U substitution, are going to be the 2 primary rules of antiderivatives. So let's look at integration by parts really quick. It ends up looking like f. Since it's a product rule, we're going to look at a product of functions, right? The U substitution is always on a composition of functions, but a product rule will be on products of functions. But one of my 2 functions needs a derivative. So I have a product of functions, but one has a derivative. Doesn't matter which one has the derivative, as long as we write the next half correctly. This will look like f of x times g of x, so g has lost its derivative, minus the integral of f prime of x, g of x dx. And so in some sense, what has happened is you have this notion of an antiderivative just on g, so g loses derivative, and it also loses a derivative here. So g loses a derivative in both cases, but f gains a derivative on a second term. So the second term there is that f has gained a derivative. A lot of times the way I like to describe this is integration by parts moves derivatives. Spell between products of functions under integrals. All right, in some sense, we've taken this derivative and moved it onto f. So it's disappeared and it's been moved onto f, but there's a price that you pay. Paying the price of the functions multiplied together and a minus sign. So in some sense, this is the price one pays to move the derivatives around. So let's look at some examples of integration by parts. It may not seem like the integration by parts formula is actually useful. Let's just write it down as a formula, that way everybody has it. You can just kind of screenshot this one part. So let's say integral f of x g prime of x dx equals f of x g of x minus the integral f prime of x times g of x dx. Just go ahead and screenshot that because we'll be using it a few times the rest of the semester. Let's look at our first example. If we want to find the antiderivative of x times e to the 2x dx, it may not seem like this is a very easy thing to do. I mean, somebody might try use substitution, but you would find out that since x is not the derivative of 2x, then you can't use substitution. You have to use integration by parts, and so have to use int by parts. And like, it helps to notice that we have a product sitting around, right? Integration by parts always has a product in it. The product sits around. So you have to use integration by parts. We need to decide where the derivative is, right? Because up here I've written g prime. We need to decide where g prime is over here. The way I've written it, I have an x on the left and an e to the 2x on the right, but there's not really a guarantee that the e to the 2x should be the g prime, because I could have always written it like this. There's nothing different about me writing the formula like this instead. And in this case, now it looks like g prime should be x. So we still have to decide what g prime should be. On which term is g prime, hence which is f would be what's left over. It's always to our advantage to choose exponentials for g prime. Now we won't always see exponentials around. In this course we basically will. It's only ever going to be exponentials that we see, but if you're taking a different calculus course, you would see some things that aren't exponentials necessarily. But it's always to our advantage to choose exponentials for g prime, so we're going to go ahead and do exactly that and say that this is the derivative of a function, making this f. We'll go ahead and erase that. And we know, now that we know what f and g are, we can just write out the integration by parts formula as f of x, g of x, minus the integral f prime of x, g of x, dx. Well, if f of x is x, we can just replace f of x with x. But we do need to know what g is over here, because over here on the left-hand side we've got g prime, so I need an antiderivative. That's going to be the antiderivative of e to the 2x. Antiderivative of e to the 2x, also known as 1/2 e to the 2x. Arrow there instead. So that g becomes 1/2 e to the 2x. And then I can subtract the integral f prime. I need a derivative of f of x. F of x we decided was x. The derivative of x is 1. So I have a 1 here, and I'm going to multiply that by g of x, which I've already computed as 1/2 e to the 2x dx. So notice if I simplify things a little bit, I end up with 1/2 x e to the 2x minus the integral of 1/2 e to the 2x. And my life gets easy because I actually know how to compute that antiderivative. It's just the integral of e to the 2x again. And that's going to give me one extra copy of a 1/2. So I'll have 1/2 x e to the 2x minus, there's one copy of 1/2 here, as well as a copy of 1/2 coming from the antiderivative of e to the 2x. So I'll have a 1/4 e to the 2x. Plus c. So this is how we use integration by parts to find antiderivatives, and in fact it's most useful for antiderivatives of polynomials times exponentials. And I don't want to spend too much time on integration by parts today. We can spend a lot more time when we go through worked examples. Because the reason I introduced integration by parts here is let's do integration by parts for definite integrals. And if you recall, the difference between definite versus indefinite integrals is that the indefinite integral is the antiderivative. When I work with definite integrals, that's where I'm going to give some boundary terms, let's say x0 and x1 on the boundary. Then the fundamental theorem of calculus, which tells me I can evaluate definite integrals by evaluating those on the antiderivative, tells me that this is f of x, g of x, evaluated on the endpoints x0, x1, minus the integral x0 to x1, f of x, f prime of x, g of x, dx. So we have kind of a second formula for definite integrals. It's really not any different. I've just added the actual definiteness of my integrals on the result. But this is what's going to allow us to construct the Taylor series. So let's construct the Taylor series. And I'll say using integration by parts. Let's notice that a function is always going to be equal to some value at an x0 plus the integral starting at x0 ending at x of the derivative of the function. And I'm just going to use the variable y in my integral because I've already used the variable x there. So this is the fundamental theorem of calculus. It just says that the value of a function is equal to, it's really, if I swapped, pulled f of x0 to the left-hand side, it says that the difference in the bounds of an integral is the same as evaluating the antiderivative of the argument of the integral. So this is the fundamental theorem of calculus. So I'm going to go ahead and rewrite this integral as the integral from x naught to x of f prime of y times the constant function 1 dy. And then I'm going to apply integration by parts with g prime being this 1. If g prime is 1, in fact it's g prime of y, because I'm integrating in the variable y, then g will be an antiderivative of 1. It can be any antiderivative of 1 I want. I'm going to choose specifically the antiderivative y equals x. And we're going to see why in a bit. If I go through integration by parts here, what I end up with is f prime of y times g of y, which is y minus x, evaluated on the bounds x0 and x. I'm going to subtract, taking another derivative of f, because that was my other term in integration by parts, against g of y, but I know what g of y is. G of y is y minus x dy, and then here's my bounds x0 and x. If I want to evaluate just this term, I can evaluate just that term by plugging in x first and then subtracting off, plugging in x0. I have f prime of x. These are going in for the variables y, by the way. I have f prime of x, x minus x, subtract f prime at x0, x0 minus x. Well, because I have x minus x, that term is 0, which makes the entire leading term 0. And I'm going to go ahead and bring this minus sign into x minus x0, in which case I'm left with f prime at x0 times, I'm bringing the minus sign inside, just flips the x into x0. So that's what the leading term looks like. And what I can get away with is running an integration by parts on this formula. So I'm going to run integration by parts again. On just the formula of minus x0 to x, f double prime of y, y minus x dy. And I'm going to apply the exact same notion where this is going to be g prime of y, y minus x, and I'm going to let g of y, the antiderivative, be y minus x squared over 2. When I run that, my integration by parts, I'll keep the minus sign around, gives me minus f double prime of y, y minus x squared over 2, evaluated on the bounds x0 and x. Subtract, but there's already a minus sign, so now it's a plus, integral x0 to x, f with 1, 2, 3 derivatives of y against g of y, which is now y minus x squared divided by 2 dy. As before, I can evaluate this entire term as minus f double prime, I'm plugging in x for both cases of y, f double prime of x minus x squared over 2. Minus minus is 2 copies of minus signs. That'll be a plus. F double prime at x0 minus x squared over 2. As before, this term is 0, so the entire leading term is 0, and I'm left with f double prime x naught multiplying by, and because this is a squared quantity, I'm going to flip the order for free because -1 squared is equal to 1, and I'm left with the following in red. We can continue, so I've got, basically I'm left with this term, and I could continue yet again ad infinitum. This means continuing to infinity. And what I would recover is, let's look at the terms that I'm evaluating, the specifically evaluated terms. That's my first term, and then I've ended up evaluating this, and then I've ended up evaluating this. And what you would see is there's always an extra term of an integral, but the terms I'm evaluating look like the following. We get f of x is f at x0, that's the top, the original term up here. And then we add the second term I've evaluated, f prime at x0 times x minus x0. And then we add the third term I evaluated, f double prime at x0, x minus x0 squared over 2. We would see that if I continued, I would get f with 3 derivatives at x0. And then we would get x minus x0 cubed over, it would be an antiderivative of x minus x0 squared over 2. So the antiderivative is going to give me a 2 times 3, because there was already a 2 there, and I'm taking one more antiderivative. We would get f with 1, 2, 3, 4 derivatives multiplied by x minus x0 to the 4th over 2 times 3 times 4, and this would just continue onwards indefinitely. Now, there is an argument that needs to be made that the integral term, I'll say an argument must be made that the integral term, since at every case we have these integrals showing up, so we have to make an argument that the integral term tends to 0 as we take infinitely many integration by parts. And we won't get into that here. You can see that if you take a real analysis course, for example. But what we actually end up having here, maybe it's not quite clear, what we end up having is a summation. This is a summation of infinitely many terms. And I can write this summation in terms of sigma. If I use sigma notation for what I've written above, I'm going to say n equals 0 to infinity. And what is that, the n refer to? This is the n equals 0 case. This is the n equals 1 case. This is the n equals 2 case, and so on. Let's figure out where the patterns are. There's a first derivative and a first power. There's a second derivative and a second power and dividing by 2. There's a third derivative, a third power, dividing by 2 and 3. A fourth derivative, a fourth power, dividing by 2 and 3 and 4, and so on. So how could we write this? It's the nth derivative. I'm taking just as many derivatives. There's really a 0th derivative up there, right? So I'm taking as many derivatives as the n value is, and then this gets evaluated at x0. I'm also using n for the power on the x's, and the denominator is n times n minus 1 times n minus 2, and so on. We have a notion of this. This is called the factorial. The factorial is denoted by the exclamation point and defined by n factorial is n times its neighbor times its next neighbor, and so on, times 2 times 1. So this formula that we've just constructed from integration by parts is known as the Taylor series for f. So just because we constructed it that way doesn't mean that that's the way we should think about it. That is maybe the easiest way to construct it. The way we should think about it is as the following. What is our orthonormal basis for the Taylor series? And also, what is our inner product for the Taylor series. Because a basis representation tells us that a function should be equal to a sum, as n goes from 0 to infinity, of an inner product of that function against some basis element, and then multiplied by that basis element. So how does that compare here? We have to establish what these are, and we have to establish what this means. So if we look at our Taylor series, what should the basis elements be? Well, it's definitely going to be the collection of objects on the right-hand side there. We do have to be a little bit careful. We would want to say something like, oh, the basis elements are x minus x0 to the nth power divided by n factorial. We have to be very slightly careful that we should pull the n factorial, at least part of it, into the other term on the left, the derivative. So really I should rewrite the Taylor series as a root n factorial over here and a root n factorial over here. In that sense, we can think about the basis elements as x minus x naught to the nth power divided by root n factorial. Okay, but what does that establish our inner product as? That's kind of a tricky thing now, because if we've identified those as our basis elements, that means that the inner product of a function against x minus x0 to the nth power over the root of n factorial should give me the nth derivative of a function evaluated at x0. So that's a very, very confusing statement to make. How could that possibly be calculated? Because we know how to calculate these functions as the inner product written as an integral as the following. Now, there's one very specific thing that I haven't included here, and that's really the question of the domain. And in this situation, the domain, we're not going to get into why, but the domain ends up being the complex unit circle. And of course, this latter term is supposed to have a complex conjugate over it. So we're not going to get into why this is the case. If you do care about it, look up something called the Hardy space on the disk, and that'll describe how this integral is actually computed. But for now, we just want to be content with the following construction of the Taylor series. So I'll write out the Taylor series now. Given f of x and a point x naught in the domain of f, the Taylor series centered at x naught is f of x equals the sum of the nth derivative of f evaluated at x0, x minus x0 to the nth power divided by n factorial. And this is a basis decomposition of f against x minus x0 to the nth power over the square root of n factorial times x minus x0 to the nth power over the square root of n factorial. It's just maybe not so clear that that's what is going on here. Anyway, what you should memorize is what I'm circling right now. This is probably one of the most important memorizations you can make for the rest of your mathematical careers, is the definition of the Taylor series. Let's just look at one example. One example of the Taylor series. Let's do e to the 2x centered at 0. What I need to do, I can write e to the 2x as a sum over infinitely many terms of a bunch of derivatives. So I'll take the nth power of the derivative, and I have to evaluate this at the center, and then I have x minus the center to the nth power divided by n factorial. Thankfully, we can take derivatives of the exponential fairly easy. 0 derivatives of the exponential is itself 1 derivative of the exponential, because of the chain rule, gives me a 2. The 2 derivatives of the exponential give me 2 copies of the chain rule, so I have 2 copies of 2, and so on. I would find that n derivatives of the exponential gives me n copies of the chain rule, 2 to the nth power. And if I evaluate each of these at 0, I just end up with e to the 0 power, which is 1. I end up with 2e to the 0 power, which is 2 times 1. 2 squared e to the 0 power, which is 2 squared. 2 to the nth e to the 0 power is 2 to the n. And so I can actually rewrite this as the sum, as n goes from 0 to infinity, of 2 to the nth power. And of course, here is x minus 0 to the nth, so that's x to the nth power divided by n factorial. And if I wanted to write this out explicitly, we have our n equals 0 case, that's just going to be 1. The n equals 1 case is going to be 2x over 1. The n equals 2 case is going to be 2 squared, 4, x squared, divided by 2. 4 divided by 2 is 2. The n equals 3 case is going to be 2 cubed, which is 8, times x cubed over 3 factorial, which is 2 times 3, which is 6. So I have 8/6, also known as 4/3, x cubed, and so on. So that's what's known as the Taylor series for e to the 2x. We're going to encounter these a lot more in the applications video coming up soon, if you feel a little bit uncertain about what's going on. We're going to finish out with our last case of today, which is the Fourier series. The Fourier series is given by, and I won't derive this for you, but in fact later this semester, you'll derive it later this semester. But I do want to provide it for you as a series that's really useful. Fourier series is given by f of x equals an infinite sum, and going from minus infinity to infinity, of 1 divided by 2 pi, the integral from minus pi to pi, f of x e to the minus I n x dx, multiplied by e to the I n x. This is equal to, in basis decomposition notation, the sum over n in the integers, the inner product of f against e to the I n x over root 2 pi, multiplied by e to the I n x over root 2 pi. And you can tell what the domain of these functions is just by looking over here, where the domain of the functions is the interval minus pi to pi. So this is the basis decomposition for the orthonormal basis given by e to the I n x divided by root 2 pi, and n is in the integers. So as before, what you should focus on here is what I've just circled, even though it is a basis decomposition. The Fourier series is really what I've circled. And let's go ahead and look at one example of this. Find the Fourier series representation for the function x. So we just look above, the function x should be equal to the infinite sum, minus infinity to infinity, of the integral 1 over 2 pi, integral minus pi to pi, x e to the minus I n x dx, multiplied by e to the I n x. So what we need to really do is compute this. We must compute this. And it'll be in terms of n. So we need to leave n undecided, but everything else needs to be computed. How could I do that? Well, let's go ahead and just focus on the integral, because 1 over 2 pi doesn't play a huge role. Let's focus on the integral minus pi to pi of x e to the negative I n x dx. What does this look like? This looks like an integral of a product. There's a reason why I introduced integration by parts today. So we need to integrate this by parts. What are we going to choose for g and f? F is going to be right here. G is going to be right here, g prime. Which means that g, I need an antiderivative of e to the minus I n x. Let's recall the antiderivative of e to the ax is 1 divided by a, e to the ax plus c. So an antiderivative of e to the minus I n x dx, what's playing the role of a here, is minus I n. So we'll end up with 1 divided by minus I n, e to the minus I n x plus c. Or because this is a definite integral, I can get away with 1 divided by minus I n, e to the minus I n x. That means my integration by parts gives me x times 1 divided by minus I n, e to the minus I n x, evaluated at minus pi and pi. Subtract the integral minus pi to pi, e to the negative I n x, and there's still a 1 divided by negative I n sitting around here. So I have one more antiderivative to calculate there, but I don't have to go through too much work because that's just another antiderivative of that form. If I go ahead and compute that one more antiderivative, what is it going to give me? Well, I already have two minus signs canceling, so I'll have something like 1 divided by I n, and then I'll have another copy of that with a minus sign from the antiderivative of e to the minus I n x, and then e to the minus I n x, evaluated at negative pi and pi. If I go ahead and perform my evaluations here, that would be me plugging in pi, me plugging in minus pi, me plugging in pi, me plugging in minus pi. Of course, over here, these end up on x as well. What am I going to get? I'm going to get pi e to the minus I n pi divided by negative I n minus negative pi e to the positive I n pi divided by negative I n. And then the blue terms as well will give me plus 1 divided by negative I squared n squared e to the negative I n pi minus 1 divided by negative I squared n squared e to the positive I n pi. Now these terms, I was missing a pi there, these terms, e to the I n pi, what should those be equal to? That's kind of always a tricky thing when students get to Fourier series. E to the I n pi, or negative I n pi, basically the same. Never forget Euler's formula. Euler says e to the I theta is cosine theta plus I sine theta. This will always allow you to use your unit circle to solve these. And so what's playing the role of theta here is n pi, cosine n pi, plus I sine n pi. And these n's are integers, so we're asking ourselves questions about the unit circle when we're working with integer multiples of pi. So this is pi, theta equals 0. This is theta equals pi. This is also theta equals 2 pi. This is theta equals 3 pi, 4 pi, 5 pi, and so on. And so we see that these only take the values at these 2 points. So we can either be a negative 1 when n is odd, or we can be a positive 1 when n is even, depending on if we're on the left or the right hand side. Well, you can get away with some shorthand of negative 1 and 1, even versus odd, by just writing negative 1 to the nth power. Because when n is even, that's negative 1 to an even power, and will always give you 1. When n is odd, that's negative 1 to an odd power, which will give you negative 1. Moreover, the sine terms, what is my y value at these points? The y value is always 0. And so we can evaluate e to the I n pi as negative 1 to the n, which means that what we have here is equal to pi times negative 1 to the nth power divided by negative I n minus negative pi, so I'll just say plus pi, negative 1 to the nth power divided by negative I n, plus 1 over negative I squared is just negative negative 1, and then negative 1 to the nth power, minus 1 divided by negative I squared is a negative negative 1, n squared negative 1 to the nth power. We can see that these two terms cancel, and these add together to give me my result, which will end up being 2 pi, negative 1 to the nth power divided by negative I n. But negative I in the denominator is the same as positive I in a numerator, and I end up with 2 pi I divided by n. So this was an evaluation of the original integral we wanted to evaluate without the 2 pi. If I include the 2 pi there, then that just cancels with the 2 pi I have down here, and I find out that my Fourier series for x is this infinite sum, minus infinity to infinity. And now I've evaluated everything. The 2 pi's are canceling. I have an I, negative 1 to the n divided by n, multiplying e to the I n x. Okay, I know that was a whole lot of work, and I hope you're able to stick with me through it. If not, you're going to get a lot more practice in the next video. I'll see you then. Bye.